All right, turn to page 175, number 34. Numerator is larger than the denominator, so it's an improper fraction. So divide the numerator by the denominator. Pause the video and give it a try. All right, now use partial fractions on this. See how you do with it. On this portion. This portion is easy to integrate. This is the portion you have to use partial fractions on. Pause the video, give it a try. Alright, so I divided through, I get x squared plus 1. Using the partial fractions, I'm going to factor this into 1 over x plus 1 times x minus 1, a over x plus 1, b plus b over x minus 1. Basically, I'm just going to cross multiply. So I get ax minus a plus bx plus b. I group the x's together. All right. There's no x here, which means the coefficient, which is what a and b represent, is 0. So divide 0 by x gets rid of the x, so a plus b equals 0. Now minus a plus b, the coefficient here is 1. So now I have minus a plus b equals 1. I add them together, I get 2b equals 1, b equals 1/2, a equals negative 1/2. So go ahead and finish it. Pause the video. All right, and this is your final answer. I put the negative 1/2 above the x plus 1, put the 1/2 in place of the b, and then I integrate it, and here is your answer here. Now if you didn't get it correct, do it over. All right, page 201, number 10, improper integrals. We're interested in whether it converges or diverges. You're going to have to use your integral tables to integrate this. So go ahead and do that. Pause the video, see what you get. Okay, if you use your integral tables, you'll find out that this is equal to tangent, the inverse tangent, negative 1x over 2. Now plug in these values and find out whether it converges or diverges. If it converges, it goes to a particular number. So pause the video and try to do the work. All right, I plug in, I'm going to get 2 over 2, so the inverse function is going to be equal to 1 minus b over 2. All right, and this is going to go to negative infinity. So the tangent function is equal to side b over side a. It's only going to be equal when b equals a, and that's only going to be true when theta is 45 degrees. So for this one, it's pi over 45. Now, as x goes towards negative infinity, even though you're dividing it by 2, this here is going to be a negative pi over 2. All right, negative pi over 2. All right, so do the arithmetic and see what answer you get. Pause the video. You can probably do this in your head, I hope. All right, you should have ended up with 3 pi over 4. Try problem number 12. Pause the video. You're going to need your integration tables to do this one. So get them out, take a look at it. Give it a try, pause the video, come back and see how you did. All right, the integration formula will give you natural log of t minus 1 over t plus 1. Now substitute b in as it goes to infinity, and then put in the 2. See how you get, see what answer you get. Does it converge? Does it go towards a number? Or does it diverge? Pause the video, give it a try. Here's what you should have when you plug in b and 2. It's going to be infinity over infinity, which is going to give you natural log of 1 minus natural log of 1, 2 minus 1, minus the natural log of 3. So finish it and see what answer you get. Pause the video. All right, plug them in. This gives you natural log of 1 minus the natural log of 1 plus natural log of 3. Natural log of 1 is 0, so it's 0 minus 0. And that means natural log of 3. So as b goes to infinity, this function converges to the number, the natural log of 3. Right, it converges. All right, I want to talk to you about the Taylor series. We have a function e of x. And what I want to do is write a polynomial that if I graph the polynomial at a particular point, it will coincide with the graph of e of x. So my first step is x is going to equal 0. When x is equal to 0, e to the 0 equals 1. I want g of 0 to equal f of 0. Right? So I take my polynomial, put 0 in for x. The question is, what must a sub 0 equal? Well, a sub 0 must equal 1. Next, I take the first derivative of e to the x, which is e to the x. When x is 0, the first derivative of e to the 0 is 1. I want the first derivative of the polynomial to have the same value. Well, the first derivative of g of x is a sub 1, which means a sub 1 must equal 1. All right, so I take the second derivative of e to the x, put in the 0, second derivative of e to 0 is 1. Now I've added a term to the original function, and the second derivative of that is 2a. So the question is, what must a equal in order that the second derivative here equals 1? All right, if you solve it, you'll find out that a, that should be a sub 2, must equal 1/2. All right, I removed an x there. First derivative, that x would have disappeared, and I left it there by mistake. So when you solve it, a sub 2 is going to equal 1/2. Now I can write the polynomial. I take the function here, rewrote it, substitute in the values for a sub 0, a sub 1, a sub 2. Now I want you to calculate substitute in P1 for x and see what you get for an answer. Pause the video, go ahead and do it. All right, you should end up getting 1.105. Now take your calculators, calculate e to the point 1, see what you get. Pause the video. All right, and you should get 1.1051709. It keeps going on. But notice down here you have 1.105. All right, that's very accurate. For some functions, you're going to want to use the Taylor series because of the difficulty of dealing with the functions. So let me go over this again with you. Have a function f of x equals e to the x. Take the first derivative, get e to the x. Take the second derivative, I get e to the x. Take a value of x equals 0, substitute it in, I get 1. I have a polynomial. In this case, just has two terms, a sub 0 plus a sub 1x. I want g of 0 to equal this. So the question becomes, what must a sub 0 be? When I put the 0 in for x, I get 0. A sub 0 must equal 1. So I take the first derivative of this, I get a sub 1. Take the first derivative here, I substitute in, I get 1. So for the first derivative of g of x to equal 1, a of sub 1 must equal 1.